Hey guys, and welcome to another video. Today we're going to go ahead and start proving some special right triangles. These special right triangles are going to be very, very crucial for the rest of the school year. They're going to be coming up in Unit 3s and Unit 4 and Unit 5 100%. So let's go ahead and dive in. So the problem reads, proving special right triangles. Prove that the side lengths of a 30, 60, 90 triangle have a ratio of a radical 3, and 2a. So what I'm going to start with, and I'm going to say, hey, let triangle ABC be an equilateral triangle with side length of 2a. So I'm going to go ahead and draw that for us. So we have A, B, C, and we're going to call each side length 2a. And we know they're all equal because it's an equilateral triangle. All side lengths are equal. This also means that angle A is equal to angle B, which is equal to angle C, which is all going to be 60 degrees, because that is what an equilateral triangle is. So I'm also going to add that into our visual. That's 60, 60, and 60. So, but right now, our job isn't to prove an equilateral triangle, but to prove a 30, 60, 90 right triangle. But right now, if you notice, I already have that 60-degree angle. So now the next concept I'm going to introduce is called an altitude. An altitude is a perpendicular line from the vertex to the opposite side. So I'm going to go ahead and draw an altitude. So I'm going to go ahead and erase this 60-degree angle real quick. And I'm going to draw an altitude from A all the way down. And there's a couple of features of an altitude that I need to share with you. An altitude does two things. It bisects the angle. And bisects means that it cuts it directly in half. So that means this angle is now going to be 30 degrees. And this is also going to be 30 degrees. And it bisects the side length. So if originally each side length was 2a, that means from here to here, this is a, and from here to here, that is a, because a plus a equals 2a. So if you're starting to notice, I have that a side length, I have that 2a side length. I'm now just missing that a radical 3. But now we also need to understand that because that altitude is a perpendicular line, this is now a right angle, and this is a right angle. So that means we now have some right triangles in this visual. So as we know, in a right triangle, we are able to do a squared plus b squared equals c squared. Or because right now we're looking for the length of the altitude, we could rewrite this as c squared minus b squared equals a squared, where I just subtracted b squared on both sides. So I'm now going to go ahead and plug in. So our hypotenuse is 2a. And one of our side lengths is just a. All these a's are complicated, I guess, right? So 2a squared is going to be 4a squared. A squared is just a squared. This is going to now equal to 3a squared. Maybe I should have used a different variable, right? These a's are confusing. Now, if I do the square root on both sides, I get a is equal to 3a squared. Remember that lesson about simplifying radicals. We can further simplify this to a radical 3. So that is now how we have all three side lengths. We have one side length is A, we have that our hypotenuse is 2A, and then we have that the height of our triangle is A radical 3. So this is a very important takeaway. In every 30, 60, 90 triangle, because we did a general proof, that means this is true all the time. In a 30, 60, 90 triangle, the side length opposite of angle 30 is always going to be A. The hypotenuse is always going to be 2A, and the side length opposite of angle 60 is going to always be A radical 3. This is always going to be true, and it's going to be very, very important that you internalize it. So for the rest of the day, what you guys are going to be doing is implementing this law and figuring out other side lengths within 30, 60, 90 right triangles. All right, have a good class.